Okay, this video we're going to cover some examples related to the lesson videos in Lesson 5 and case compound event probabilities, and also the idea of independent events. Okay, so the first problem here says a jar holds 10 white, 4 blue, and 6 red marbles. If 2 marbles are chosen with replacement, meaning that when we choose a marble, we record the color, and then we put that marble back. We replace that marble and mix them around before we choose the second one. What's the probability that they will both be red? So with the video, go ahead and pause that, give it a try, and then unpause the video, and you can see whether or not you got the question right. Okay, so the first thing I would notice is, since we're talking about both being red, that means that the first one is red and the second one is red. So this is definitely an AND case probability. And that means that we're going to be doing something where we're talking about the probability of the first one being red and the second one being red. It's an AND case probability. And that would be equal, therefore, to the probability that the first is red times, because AND is multiply, the probability that the second is red, given that the first one was red. Remember that with AND probabilities, the second probability is always supposed to be a conditional probability. Okay, so what do we have? We have a jar with 10 white, 6 red, and 4 blue marbles. We're going to draw one out, and so that means there's a total of 20 marbles there. So this first probability would be out of the 20 marbles. That's the sample space. The event would be drawing a red marble, and there are 6 of those, and they're all equally likely to be chosen, all 20 marbles. So this is an equally likely case. It's just the number of red marbles over the total number of marbles, so 6 out of 20. Right now, we drew that marble out, but then we put it right back in. We're replacing it. So we have the exact same setup here when we do the second probability. So the second probability, we also have the original 20 marbles, and again 6 of them are red, so that means 6 out of 20 is the second probability. And we would multiply those two and get 36 out of 400, or this is 0.09. So the probability of getting both red, if we draw 2 marbles with replacement in between, would be about 9% chance. Okay, let's try the next problem. So the next problem is almost the same. It says the jar holds the same 10 white, 6 red, 4 blue marbles. This time we choose the marbles without replacement, meaning we'll keep whatever marble we got the first time out, and then we'll draw from the remaining marbles for the second one. And we're again finding the probability that both are red. So again, this is a compound probability. We're talking about the probability that the first marble is red and the second marble is red, which is the probability that the first is red, and then times the probability that the second is red, given that the first one is red. The second probability is supposed to be a conditional probability. And we have the same 10 white, 6 red, and 4 blue marbles in there, 20 marbles. And so the first probability would again be out of the 20 marbles, 6 of them are red. So 6 out of 20 is the first probability. And this time that means that when we draw one of the red marbles out, we have now 10 white, but now only 5 red marbles left with the 4 blues, which means there's now only a total of 19 marbles in the jar. So when we go to do the second probability, because we didn't replace it, the conditional probability is, given that we had a red the first time, this is now what's in the jar. And so now the probability is, out of the 19 remaining marbles, what's the probability that we'll get a red one? So that would be the 5 remaining reds out of the 19. So the probability changes. These probabilities are not independent because the probability of the second one depends on what happened in the first. And so if I multiply across there, 6 times 5 is 30, and 20 times 19 would be 380. And so that turns out to be 0.0789. So a little bit less than 8% probability. It's less likely of getting red the second time because there's less reds in the remaining marbles. Okay, so that's the first two problems. Let's go ahead and move on to the next one. So this one says a fair 10-sided die is tossed 3 times. What's the probability that we get a 7 all 3 times? Okay, so again, that means we have to get a 7 the first time, and a 7 the second time, and a 7 the third time. And so this is an AND case probability, so we're going to multiply. The probability that all are 7 would be the probability of getting a 7 the first time, and then times the probability of getting a 7 the second time, given that we got a 7 the first time. I'm going to write it like that. And then times the probability that we get a 7 the third time, given that we had a 7 the first 2 times. I'm just kind of using an abbreviation here to indicate that. But this means the probability of a 7 the third time, given that we had 7s the first 2 times. The thing about it is that with a die, what happens on each roll is definitely independent. There's no memory in a die or anything like that. It's not like the jar where when we pull a marble out, it changes the probabilities in the remaining balls in the jar. The probability of getting a 7 is going to stay the same every time, right? So I think I could just say because these are independent, the rolls are independent, then that means that this is just going to be the probability of getting a 7 when I roll the die, and the second one is just going to be the probability of getting a 7, and the third one's also going to just be the probability of getting a 7. Each time I roll the die, it's like an independent thing, right? So for the die, we have a sample space of all the possible results we could get, which would be we could roll a 1, a 2, a 3, a 4, a 5, 6, 7, 8, 9, and 10. And then the event would be specifically that we got a 7 only. Right, so that means that for each of these probabilities, we're going to be taking out of 10 in the sample space, 10 possible outcomes. Only one of them is a 7, so the probability is 1 out of 10 of getting a 7. And each of these would be the same because the probabilities are independent. They're not changing. And so this ends up being 1 times 1 times 1 on the top, 10 times 10 times 10 on the bottom, which is 1,000. And so this would be 0.001, a very small probability indeed. And that's because there are so many different things that can happen if there's 10 different ways to roll the dice each time. All right, so that's that problem. Let's move on to the next one. Next one has a table of information that asks a lot of different questions. So it says a sample of 100 people at a mall were asked to try 2 different soft drinks and state their preference. So there's drink A and drink B. And then we also have the numbers separated by males and females. And there's a number of probabilities that are asked about. And then the last question here is about independence. So I would ask you to pause the video, read through these and try each one, and then unpause. Okay, so when I solve this problem, the first thing I would do is I would go ahead and add up the totals and the margins here. What's the total number of males and females? So that would be, let's see, 22 plus 38. That's going to be a total of 60 males. And there's 22 plus 18, which is 40 females. So there's a total of 100 people in the sample, which we know because it said that in the problem. That's a 100 there. Okay, and then as far as drink A, a total of 44 people preferred drink A and a total of 56 people. If I add 38 and 18. So it's always good if you have a table to find the marginal values if they're not already provided. Okay, so let's take these one at a time. What's the probability that a person selected at random from this group will prefer drink A? So the way I could write that statement would be this way, the probability of liking A. Right? There's no conditions or anything like that. It's not a compound probability. It's just a simple probability. And so that means that every person in this sample is equally likely to be chosen if we choose a person at random. So it's an equally likely case. We'd be talking about 100 people to choose from because it's the entire sample set. And out of that 100 people, how many people prefer drink A? That would be this 44. So it would be 44 out of 100 or 0.44. That would be the probability of someone at random being chosen who likes drink A. Okay, for part B here, we're talking about, again, a simple probability. This time, it's the probability that a person selected at random will be a female. So it's just the probability of selecting a female. And again, this is a simple probability, so it uses the entire data table. That means out of the 100 students, how many of them are female? Well, that would be 40 over here, 40. And so that probability is 0.40. A 40% chance of choosing a female if we choose one student at random. So far, so good. Okay, so part C then asks, it says, what is the probability that a person selected at random will be a male and prefer drink B. Okay, so this is a little different, part C. This time we're saying that they have to be a male and B. So the way I could write that as a probability statement is we're finding the probability that a person is male, and I'll use the and symbol, that they like drink B. Right? Now this is not a conditional probability, and that means we're still talking about selecting out of the entire 100 students, right? Or people at a mall. But to be in the numerator here, to be in the event, we have to be male and also B, which is the intersection of the male row with the drink B column. So male row, drink B column intersects right here. It would be these 38 people. So 38 people, right? And so 0.38 is the probability of a selected person being a male and also drinking B. Now, we should be able to also do this problem using the AND rules, right? Because we know that it's multiplying probabilities. So, right, another way to do this, a completely separate way to do this problem, would be to say the probability that somebody is a male and likes drink B, we can pick one of those and say probability of being a male, and then multiply by the probability of the other thing, but conditionally, the probability that somebody likes B given that they are a male. Remember, the second one in an AND always has to be a conditional probability. So what would that look like? Well, the probability of being a male is a simple probability, right? That's out of the entire 100 people. How many of those people are males? That would be 60. And then the second one would be a conditional probability, which means this right here determines the bottom of the fraction, so only the males. So out of the 60 males, what's the probability that only out of the males they like drink B? And that would be the 38 number. So 38. And so when I multiply, these two 60s will cancel and leave 38 out of 100, which is that same 0.38. So that would be another way to find it. And also, I chose to use the probability of male first, but we could also write it this way. We could also say the probability of male and B is the probability that somebody likes drink B times the probability that they're male given that they like drink B, right? You can use either one as the first event, the one that's not conditional. So in this case, the simple probability would be out of the 100 people, how many people like to drink B? So that would be 56, right? 56. And then this would be a conditional probability. This time the condition is being established by B. Given the condition that they like drink B, which is the 56 people, how many of those people are male, which is 38. And so again, the 56s will cancel out and leave 38 out of 100 equals 0.38. So if you did this problem any of these three ways, those are all perfectly good ways to solve the problem. Okay, so let's go ahead and I'm going to erase this, and we'll move on to the other problems here. Let's get an eraser. And we'll just erase this whole thing. All right, so let's try part D. Part D says, what's the probability that a male from this group will prefer drink B? Okay, so this part, that a male from this group, is specifying some condition, right? In my mind, it's really specifying the condition. You could almost think of it as a parenthetical comment. If I temporarily crossed it off, the sentence is really asking, what's the probability that somebody will prefer drink B? So D here is a conditional probability, right? But the male from the group part is really the condition. So this could be written, the probability that somebody likes drink B given the condition that they are male. And that means that we're talking specifically about a conditional probability, so the bottom of the fraction is not the entire table, it's just the males. Remember, the bottom establishes the denominator. So out of the 60 males that we have, out of the 60 males, how many of the males also like B, right? So within the male column only, right, 38 like B. So it'd be 38. But this time it's 38 out of 60. And so that probability is 0.6333. Okay? So a conditional probability. Okay, let's look at E. E says, what's the probability that a person who likes drink B is a male? Okay, a person who likes drink B is the condition, because really this is asking what's the probability that someone is a male. So we're finding the probability that somebody is a male given the condition that they like drink B. So this is the condition but in the other direction. And that means that the bottom of the fraction will be all of the people who prefer drink B, which is 56. And the top of the fraction will be the people in the B column who are male, which is 38. So this will be 38 out of 56, which turns out to be 0.6786. So you got this problem correct if you did that. The main thing is the bottom of the fraction changes. Okay, and then the last thing said, are the events female and preferring drink B independent? I'm going to change colors here for the pen. So there's actually three ways. There's a number of ways to test this. The best way to test for independence, I think, is to pick one of the two cases here. Like, for example, I could check this one, that they prefer drink B. And then we're going to find all the different probabilities of ways to prefer drinking B, right? So we could just ask for the entire data set, how many people prefer drinking B? Well, that would be out of 100 people, right? 56 of them prefer drinking B, and so that would be 0.56, right? And then I can pick another way to find preferring to drink B, which is we could say, what's your chance of preferring to drink B if you are, say, for example, a female, given one of the conditions of the other variable? Well, that's a conditional probability, and so that means looking at just the females, there's 40 females, how many of them prefer drink B? That would be 18 in the female row. People that prefer drink B, that's 18. Right? And so that turns out to be 0.3214. And since those probabilities are not the same, that means liking drink B depends on your gender, because it's different for females compared to all the people. We could also have chosen to do the probability of B given male, and that would give me some other value, right? That would actually turn out to be 30, let's see, out of the 60 males, 38 prefer drink B, right, which we found above is the 0.6333. So you only have to check any two of those. And in this case, if they're not the same, then we would say because the probability of B is not the same as the probability of B given, say, female. Sorry, I'm running on a tablet here, so towards the bottom it's kind of iffy. Then we would say that these are not independent, right? It, in fact, depends on gender, right? Liking B depends on gender. Now, I chose to evaluate the probability of B occurring, right, drinking B, but I could also have done it by evaluating female. Let's check the probability that somebody is a female, right? We calculated that before. It's just out of all 100 people, right, 40 of them are females, so that's 0.40. And then if I take what's the probability of being female given that you like drink B, the other event. So this would be out of the B drinkers, 56. How many of them are female? That would be 18. And 18 out of 56 turns out to be, let's see, female given B. Let me check this because I think I might have made a mistake in the other one there. 18 divided by 56. Yeah, this one's 0.3214, which I think means I made a mistake back here. I'm going to change something over here. So what is 18 divided by 40? Yeah, I wrote the wrong number down for this one. This is 0.45. Same result, though. Probabilities are not the same. Okay, so here, the probability of female, given that you like drink B, is only 32%. And since 40% and 32% are not the same, right, since the probability of being female regardless of what you like to drink, is not the same as the probability of being female given that you like drink B. It means that being female and preferring drink B are not independent. Right? So that I think using one of those two methods there is the best way to check it. Okay. Now there is one more way to check this. Let me erase this part of the screen, and we'll try one last way. Erase this part over here. Okay. So the books, some books include a formula, right? They say, so let me derive it. We know the AND formula for this would be the probability of, let's say, B and female is equal to the probability of B times the probability of female given that you like drink B. That's the true AND formula. The second one has to be a conditional probability here, right? But if these were independent, then this one would simplify to just being the probability of female. In other words, if it was that these were independent, then the probability of female given B would be the same as the probability of female. So some books, they give this formula, B and female. The probability of B and female is so you can check it. If it's equal to being the probability of B times the probability of female without it being conditional, then that means that it is independent, because that only time that will work is if these are independent and these are equal. So we could do that. We could say we found the probability of B and female, right? We found that. Have we done that? No, let's find that. The probability of B and female would be out of the 100 people, because it's a simple probability. You have to be in the female row and the B column, which would be 18. So that probability is 0.18. And then we're checking, is that equal to the probability of B, which means out of the 100 people, the probability that you like B is 56, times the probability of being female. So out of the 100, that would be 40. And when we multiply those out, we actually get 0.224. Since those are not equal, that's a third way to test and determine that these are not independent. Okay, but actually I prefer this method, right? Because that gets at the heart of what being independent really is about. Okay, nice big problem there, lots to think about. Let's move on. So this question, it says a student has an 80% chance of passing their English final and an 85% chance of passing their math final. What's the probability that they will fail both their English and math finals? So go ahead and pause this and give this a try. Okay, so first of all, since this has to do with the probability of failing, I think we should first figure out the probability of failing English and failing math. So that independently, the probability that they're going to fail English is going to be 1 minus the probability that they pass English, right? So the probability of failing English is going to be 1 minus, well, there's an 80% chance of passing their English final, so 0.8, so that's going to be 0.2. Let me erase that. It's really getting hard to see this. Okay, so the probability that they would fail their English final is 0.2. Okay, and the probability of failing math, I'm going to use M for math, will be 1 minus the probability of passing math, which is 85%, they say. And so that would be 0.15. So let's first start by finding out the probability of failing these two things. Okay, and then let me switch colors here. Let's go ahead and figure out what the probability is that we do want. We want the probability that they fail both. They fail English and they fail math. Okay, since that's an AND case, that's going to be equivalent to the probability of failing English times the probability that they fail math given that they failed English. Okay, Now, we're going to make a simplifying assumption here. We're going to assume that whether they pass or fail each class is independent. In other words, if they pass their math test, it doesn't mean they're more or less likely to pass their English test, and vice versa. Now, that may or may not be a good assumption. There could be other things at play here, like maybe they didn't get a good night's sleep before, or they're sick, or something like that. And so, if they're likely to fail their math test, they're also likely to fail the English test. But let's make an assumption that that's not true and that they're independent. So if that's true, then this would just simplify to the probability of failing English, and then this conditional probability could just be the probability of failing math, and I don't have to put the conditional part on, because what I'm saying is the probability of failing math given that you fail English is just the same as the probability of failing math, period. Okay, and we just figured out what the probability of failing English was. That's 0.2. And we also figured out what the probability of failing math is. That would be 0.15. And so now we can multiply those two things to get 0.03. So it looks like only a 3% chance that this student would fail both their tests. Okay, so let's move on. There's just a few more to go, 2 more to go. So this one says 6 letters with repetition allowed are selected from the alphabet. What is the probability that none of the letters are repeated? Okay, go ahead and pause this. Think about it for a sec. Try it, and then unpause. Okay, well, I actually can think of 2 different strategies that we could use to solve this. One of them is easier, I think, and one's harder. We'll start with the easier one, and that is to assume that they're equally likely, that every possible selection of letters is equally likely, right? So if I kind of use that approach, the equally likely cases approach, then I'm just going to count entire words. In other words, every possible 6-letter word is equally likely. And so my sample space would just be the number of ways to get 6-letter words, to just have 6 letters, regardless of whether there's repetition or not. And a good strategy for that would be the multiplication principle. We can say there are 6 choices to make, so I'll make a box, 1, 2, 3, 4, 5, 6 for each of the choices. And then I'll go back and fill in each box with the number of ways to make the choices. There are 26 letters in the alphabet, so there would be 26 ways to choose the first letter, 26 for the second, 26 for the third, and so on. All of these would be 26. And then the multiplication principle says I would multiply each of those together. So I have 26, and then 26 6 times. You could also write it this way, 26 to the 6th power. If you do that in a calculator, that turns out to be 308,915,776. So there are over 308 million ways to have 6-letter words if we're allowing repetition, right? So 6 letters with repetition allowed are selected from the alphabet, and that means that that's going to be on the bottom, the numerator of our equally likely case. So when I look at the event, the numerator, it's going to be specifically the number of ways to pick distinct letters, to pick different letters. In other words, this is a probability, different letters. This is what's the probability that none of the letters are the same. So I have to go back and count how many different words are there that don't have any repetition of the letters. So I'm going to use the same thing, the boxes, 1, 2, 3, 4, 5, 6 choices to make, right? And I can use all 26 letters for the first box, but once I've selected a letter, then I can't select that letter for the second part of the word. And so there's only 25 letters remaining. And then 24 letters left because I can't use either of the first 2 letters. And then I've used up 3 of the letters, so now there's 26 minus 3, or 23 letters left. I use up 1 more, and then 1 more, and we would multiply all of those together. So it turns out that the number of words that have no repetitions in letters is 165,765,600. We got that by multiplying those numbers together. And that's going to be the numerator of the fraction. So the probability here, the probability we're trying to find, would be 765,600 as the numerator, and then it'll have the 308, 915,776 number as the bottom. And when you put that in a calculator, that turns out to be 0.5366. So just over 53% chance that if I pick 6 letters from the entire alphabet every time, repetition allowed, there will be about a 54% chance that none of the letters would be repeated. Okay, so that's a good strategy to do it. There is another strategy we can employ. Let me switch colors here. So a different strategy would be, instead of thinking of the entire word at a time, maybe we could consider each letter as an individual part to analyze. And we'll use, somebody say we're going to use the AND rules here because we're going to consider each letter individually. Okay, so the probability, maybe I could write it this way, the probability that all the letters are different would be, first we have to have the probability that we have a letter, right? And then we'll multiply by the probability that we have a different letter. And then we'll multiply that by the probability that the third letter is different from the first two. And so on. We'll do that for every one of the letters, right? So, well, the probability that we get a letter is 1, right? If we pick a letter from the alphabet, we're absolutely certain to get a letter, right? So the first letter's probability would just be 1. And the probability of the second one that it's different would be, okay, we have 26 letters to choose from, but we can only choose 25 of those. That would be the probability that the second letter is different than the first one. And then the third one would be, okay, we still have 26 letters, but now we can't choose 2 of them, whatever was first and whatever was second, so there's 24 left. And then the fourth letter would be 23 letters left to choose from out of the 26. Probability that the fourth one is different than the first 3. The probability that the fifth one is different still would be, out of the 26 letters, we can only choose 22 of them. And then the last one, out of 26, 21 letters remaining after we've accounted for choosing 1, 2, 3, 4, 5 already. And so if you think of this one right here as 26 over 26, you can see that it exactly replicates the structure over here. So in fact, this is going to give me the exact same 0.5366 value. So 2 different ways to think of it. You can think of it as equally likely cases and consider the words as entire words, or you can consider it picking a letter at a time and do the probability that each letter is different than the previous letters in the word. Okay. So there's one last problem. Let's go ahead and move on to the last one. We'll read it. It says, if 2 cards are drawn from a standard deck of 52 cards without replacement, so we draw 1 card, we don't replace it, and we draw a second card, what's the probability that the first card is black and the second card is a 7 if we know that the first card was not a 7? Okay, so pause this, give this a shot. Okay, the last one here, the way I would solve it is, let's just kind of consider at first, right, we're talking about this is an AND situation, right? What's the probability that the first card is black and the second card is a 7? So this makes this an AND probability, right? Let me write that. We want to have the probability that the first card is black, right? Now we have additional information that, and also it was not a 7. So I'm going to put it this way. First card is black but not a 7, and that the second card is a 7. Second card is a 7. That's what we're finding. The probability the first card is black but not a 7, and then the probability that the second card is 7. So since this is an AND situation, it means this will be equal to the first probability, the probability that the first card is black but not a 7. Right, that's a B. Okay, times the probability that the second card is a 7, given that the first condition was met, that the first card was black but not a 7. Okay, so let's view each of these. In the first one, we have a deck of 52 cards in it, right? 52 cards. We're talking about the probability that the first card is black, but it's not a 7. So if you look at a deck of cards, right, 26 of them, half of them are red, and 26 of them are black, right? But so at first glance, it seems like this would just be 26 out of 52 or half, except that we're told that this first card is not a 7. So there are 2 black 7s in the deck. There's the 7 of clubs, and there's the 7 of spades, right? So that removes 2 more from consideration. So if I take the 26 black cards, and I take out just the 2 cards that are black 7s, that means there's really 24 cards in the deck that are black but not 7 out of the 52 cards. So that first probability would be 24 out of 52. Then we're going to multiply the probability that the second is a 7, given that we chose one of these 24 cards, right? Okay, so if we chose a card, then the remaining cards, there would be 51 cards remaining in the deck to choose from. The question is, how many of those would be a 7, right, if the first card was not a 7, right? First card was not a 7. Okay, so if the first card was not a 7, then that means that all 4 7s are still in the deck, right? There's 7 of hearts, there's a 7 of diamonds, there's a 7 of clubs, and the 7 of spades. And we said that we definitely didn't choose a 7 the first time. So that means all 4 of those cards would be left, right? 4 out of 51. So then we can multiply this out. On the top we have 96. And on the bottom we have 52 times 51, which is 2652. And in decimal, that turns out to be 0.0362 approximately. Okay. So that's all I have for you as far as examples for this. There are more examples that use the AND rules in the later video that covers AND and OR together, because the truth is we often don't have cases that are purely OR or purely AND. So there's only 7 examples here, but I think there's 18 or 20 examples in that video. So if you're looking for more cases that have AND, then check out the lesson videos that combine AND with OR.